Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about human missions to Mars. So let's dive right into it. Now, first thing we have to understand what are the exact problem, because most average Joe do not understand the significance of the problems that we have to deal with. For example, Mars is very far away. What does that mean? That simply means even if you are traveling at light speed, you will reach moon in less than 2 seconds. That's very close. Now, Mars, think about 20 minutes. Let that sink in. At light speed, it will take you multiple minutes to get to Mars. So that is a very big deal. So that's why, like, many times, oh, we went to moon, then we go to Mars. No, moon is like your backyard. Mars is next country. So fundamentally speaking, it's very far away. On top of that, Mars has nothing. Like, many times people, when we talk about the time it requires to travel to there, I'm not talking about doing anything on Mars. I'm just talking about the travel time from Earth, low Earth orbit to basically Mars. That puppy is around a minimum 7 month. That is around 210 days, something like the you when you have home transfer matter, and that's another aspect of it, that we can't just go whenever we want to go. It's like, imagine it this way: we have a lunar mission, and something goes wrong, and it's like, no, we need to recover the astronaut as quickly as possible. Okay, can we do that? Yes. Will it be optimal? No. But will we build a rocket powerful enough to do that regardless? Absolutely, all rockets could do that. So fundamentally speaking, that's a very big thing, that you have to wait for 2 years. So any accidents, any supplies, in any, basically everything is limited. So that is just not acceptable for human mission. So this is the whole aspect of it. People do not truly grasp what does it mean to be basically zero G for around 7 or 9 months. So one thing you have to understand, zero G looks awesome. Everybody, hey, I want to have zero G. People are paying to get zero G just for a few minutes, and heck, I would pay for it if I was rich enough. But reality is, it's really not good for your body. Few minutes your body is like, I don't get it, was just a thrill ride. But like, the moment you start to stretch it to weeks, months, your body starts to degrade, and you will start to feel side effects of it, which may include the fact that you will not be able to sleep. So let that sink in. And having poop is also very difficult. Having sex, forget about it. So all those things are very difficult inherently. And the longer you go, like for example, 1 month your body is like, I will still ever to recover. 4 months is like, bro, I can barely hold on to it. 8 months, yeah, you need stretcher when you are going back to Earth. Now that will happen on one way, like the 7 to 9 month thing, that will happen on one way, that when you are going to Mars, you will be that crippled. So on Mars, how the heck you gonna land on it? It's like, think of it this way: you have to jump. Here's the deal. Or if your bones were a normal density, it's like you jump it, Mars is like, I can't break you. But if you are weakened by zero G for that long duration, your bones will shatter like glass. So that is fundamental danger. So you cannot have zero G. You have to have spin habitat. Otherwise, do not even think about this sort of thing. Like, it looks cool, but it's really bad for you. And again, you want to poop, you want to sleep, you want all those things. So fundamentally speaking, is one thing. Another aspect is deep space radiation. When you are on any celestial body, be it moon or be it Mars, you do have the advantage of big ass celestial body below you. What does that mean? That means if I'm standing here, and let's say the whole of space becomes radioactive, I'll be only exposed to 50% of. Why? 50% is below me. 50%, there is a giant celestial mass that is stopping all the radiation coming to me from sun, from every other cosmic source. So when you are on basically moon, same thing applies. Sun can cannot directly penetrate the solar radiation, as in like extreme gamma radiation cannot directly penetrate through whole of the moon and then reach you on the other side. It can't do that. And Mars is much bigger than moon. So anytime you are on any celestial body, radiation doses goes down. So you want to be on Mars as quickly as possible, but you do not want to be in complete vacuum for long duration. And radiation has this cumulative effect. So even though you can be survive short duration without any issue, even short duration of high exposure, but if you stretch that puppy for days, 100 days, 200 days, even the healthiest person will start to fall apart. And there could be a very weird side effect, because our reproductive system is very vulnerable to radiation. So you could literally have hundreds of healthy people, hundreds of healthy couple, and yeah, all of them are infertile. Yeah, forget about human colony on Mars. So there are some serious problems that we have to solve. So this 200 plus days of travel time, that's just unacceptable, unless you want to like send sterile old people there. Then we come to another aspect. People are like, there's a lot of excitement about Starship. One thing you have to understand, Starship is simply a bigger rocket. It's still a rocket. It's still the same principles of operation that is used for every rover that we are sending there. So it will still take 7 to 9 months. So that's not much faster. That still has that radiation issue that you have to deal with, still has the zero G issue that you have to deal with. Now you may be like, what about refueling it? Well, you have to understand, refueling is not done so it can go further. Refueling is done so it can do what we call injection burning. This whole system, Starship as a whole system, is only built for low Earth orbit. So it runs out of propellant the moment it goes to basically space, or it has some reserve propellant in order to land, but it's basically empty by the time it's in low Earth orbit. So refueling it extends its capability. Now, why do it this way rather than building one bigger rocket? Well, benefit of this does not compromise payload capacity. For example, if you take Saturn V, it's like 150 ton to low Earth orbit. Awesome. But moon, no, it's not 150 tons, it's few tons. So that's the problem with this system. If you do not refuel it, your tonnage goes down. So can Saturn V send something to Mars? Absolutely. Heck, I'm pretty sure it would send much bigger rovers than we are sending right now, but payload capacity would be much lower. Now imagine sending 100 tons to Mars. That's a completely different ballgame. That's why we had to refuel it. First, it will inject enough fuel into it so it can do injection burn on empty tanks. Basically, like it was empty when it came to space, now it's full, then we can do burn again till the tanks are almost empty, or preserve some amount for landing burn, because there is no atmosphere that will provide you enough braking. There is an atmosphere that will apply some of the slowdown, but it does not have enough where you can, like, no, it can slow down to almost crawl. So it still would be very fast. It still would need to rely on engines, and that's the another aspect, is how the heck you're gonna land on engines without having a landing pad. And 100 ton for moon, that's GG. 100 ton for Mars, when you are talking about years, not enough. Like, think about this way, like, we cannot recycle carbon dioxide. All we do is extract it. The best we can do, even if you are talking about MOXIE, is like have one part of oxygen molecule recovered. You can MOXIE does not recover, like, it takes carbon dioxide and it's like, okay, oxygen separate, carbon separate. All it does is like oxygen molecule separate, carbon monoxide separate. So you're still losing one oxygen molecule. Now imagine a few people, like say 10 people, 20 people, however people you want to put it. I'm pretty sure nobody's going to put 100 people in it. So however many people that you are putting into it, and that breathing, normally oxygen you can carry, the carbon dioxide you will start to lose over time. So fundamentally speaking, it's much more difficult. That 100 ton is no longer impressive when you're talking about Mars. It's awesome, it's GG when you're talking about low Earth orbit. When you're talking about moon, it's great. The moment you talk about Mars, it's not good. And that's why, like, when you look at the older presentation of Starships, where they actually wanted to do, they had this, their current plan is still the same. It's like you have to have hundreds of Starship in order to go to Mars, to colonize it, because one is not enough. 100 ton is just nothing, less than nothing. Then we come to another aspect. So, okay, if chemical engines are not powerful enough, then what can we do? Because Raptor is almost at upper maximum that what we can build. So nuclear electrical rockets are the only solution. Why? Well, the first thing people think about nuclear is a lot of energy, a lot of thermal energy. So why not make nuclear thermal rocket? Well, people tried to build it. There was an actual project, actual rocket engine that was tried to build, and it did work. But the problem is, it is way too close to red line. What does that mean? That simply means this: everything in that chain. When you have a giant tank of liquid hydrogen, which, mind you, hydrogen leaks too easily and hydrogen boils off too easily. So making sure your tank is, like, at full power for long enough time, good luck with that. And another aspect is, every aspect of the chain was too close to red line, meaning the reactor was as hot as they can get it. That's the only way you can get most power out of it. Fundamentally, you are almost at the melting point of metal. You have to make sure the hydrogen is running. That is the cooling system. So you get the point. Everything is almost at, like, safety margin of 80%. It's like, if minor issue happens and power spike happens to 20%, we did. So the reality is too close to red line. Can it be done? Yes. Should it be done? Hell no. So nuclear electrical can even bypass it and simply be like, okay, rather than running at like 2000 degrees Celsius, we can run at 800 degrees Celsius, and it will still provide higher specific impulse, because we can take electrical energy, couple it with ion engines like this puppy, which we have actually built, and it just has been flight tested, actually been in space and have survived long years, as in almost decade long flight missions. We know it can achieve very high specific impulse. Translation would be that if you launch it, once you do the injection burn, you start this engine, this puppy can easily shrink down your time from basically around almost a year, let's just say, to few months. And if you have a lot of electrical power and a lot of xenon gas or whatever gas that you want to use, you can even use low budget gas. You can still reach a point where you can, in principle, in real life, as in, like, if we have the tech that can do that, we just have not built an engine that is that powerful. You could achieve few days, as in like 30 days is feasible. And at that point, even 0G, you don't even need spinning habitats. 1 month your body can handle it without being degraded too much. So that's why this is the only feasible option at this point in time. Now we need a lot of reactor, lot of reactors. On top of it, there is another problem with that. You need a lot of radiator also. Now radiator is one of the limiting factor. When you are talking about making a nuclear power plant, you can make it as powerful as you want, because you can dump the cold thing into Earth's atmosphere. Earth can cool it away. In vacuum, you need giant ass radiator for that, and that is very difficult and problematic. So that would be the final limiting factor. It's like, yes, you can make a reactor that's like 50 megawatt of power, but do you have the cold sink that can sink that kind of energy? Most likely not. So that will be the limiting factor. Now, even though we are planning to actually building ion engines that are like multi kilowatt, as in like 3 kilowatt, 4 kilowatt, or some designs are going up to megawatts of power, it still has very low thrust. What does that mean? That simply means you still need to have normal rocket engines, but again, it will be only for acceleration and deceleration, because again, you do not want to go into Brachistochrome burn, where you're like 50% of journey you're accelerating, 50% of journey you're slowing down. You don't want to. You're gonna accelerate as fast as possible and use as big of a boost as possible to slow down to get captured by Mars. So that's the only feasible option right now within known technology that will allow humans to go there without suffering severe damage from radiation, severe damage from zero G, and of course, reduce the amount of materials that you're going to consume, as in like the amount of food that you're going to consume during the transition. Think of it this way: ISS needs continuous resupply. You're not going to resupply the crew on these sort of voyages, so you want to make sure the supply time is like as quick as possible. Then we come to, okay, if nuclear system is that powerful, is NASA working on any sort of system? Well, yes, they are working on kilo power system. Now RTGs are very good option, and we have been using it for voyagers and things of that nature, and they work. But problem is their output is too low. Now I can easily see all future Mars bases to have RTG as a backup for communication or some critical thing where we are like, dude, RTG is gonna take care of that, so because RTGs have very high reliability, and we have tested them for 40 years, so we know for a fact that RTGs is like put it once and forget about it. So people will use RTG as a backup, absolute critical system. But in terms of mean electrical load, you need something more powerful. So NASA is working on something like this, and the petals that you are saying, that is basically the heat sink aspect of it. Because I specified on basically space, you need giant ass radiators, a radiator that will make ISS radiator looks tiny in comparison. So NASA's kilo power reactor that they have actually built, technology demonstration has been actually built and activated. It was designed, the target is 1 kilowatt of electrical power to 10 kilowatt of power. That's why like it's kilo power. It's only going up to 10 kilowatt. Now that's a lot of power. Now what about thermal power? It has 4 kilowatt of basically it's talking about 25% conversion efficiency. So from nuclear power point of view, you are getting upwards of 45 kilowatt of thermal power. Now you may think we're gonna use that power to cool, you basically heat something. Not really. You don't need heating in Mars. Like fundamentally speaking, the sole reason we need rovers to heat, because rovers don't internally generate heat. Our body, we generate heat. Like Matt Damon, when he was like freezing in rover, that's never gonna happen, simply because if he has a spacesuit is a very good insulator. We have built spacesuit. We have spacesuit that are actually went to moon, actually been to low Earth orbit. Yes, the biggest risk at that point in time to astronaut is thermal damage, because our body is constantly radiating a minimum of 100 watt of thermal power, and if you're not dumping that 100 watt directly into vacuum, or you can't do that, radiation surface area is not enough, you will literally get heat stroked. So when he was like, that was the most silly thing I saw. It's like he is wearing a freaking spacesuit inside a space sealed basically rover, and he's like, oh, it's so cold. No, you will literally get thermal heat stroke. So, and that's why like all the spacesuits literally have liquid running through them to keep the astronaut cool. Let that sink in. We have to spend energy to cool the astronaut, not to heat them up. So this heat is not that useful. However, there are some benefits, because we want to do a lot of industrial processing. Basically, if even if you want to print basically stuff, we may need heating. This sort of energy, thermal energy, can be carried there for some use, either by use heat pipes or some conductive fluids, or some other process where, like for example, in Moxie needs to be hot to very high temperature. This radiator can directly dump its energy into Moxie, so Moxie becomes more efficient. Rather than using electrical heating, it will use this heating, and it will just use electricity to, it will become more efficient. So that energy is useful, and if done correctly, we could literally have a scenario where you are like getting more out of it, utilizing that energy. So how the heck this puppy works? Well, first thing first, they does not use water, because water has the tendency to go boom and under high pressure, and in worst case scenario can literally dissociate. What does that mean? That hydrogen and oxygen goes I got divorced. And then they make love again, and then it goes boom. It has happened more than enough time at this point in time. So water was no go. So sodium was selected. Now benefit of sodium is that sodium becomes liquid at very high temperature and remains liquid for very high temperature even still. So what does that mean? That simply means even if a reactor goes to what we call a runaway, basically there is no control system, sodium will still not reach a point where it will literally cause sodium to become vapor and pressurize and go boom. So that's the system, and it will use Stirling engine to convert the thermal energy into electrical energy. All this system has been built and tested, and the target point is around 1.5 ton. Like this whole puppy should weigh around 1.5 tons to generate around 10 kilowatt of power. That tech is ready. Be mindful, has been actually built, actually tested. Tech is ready. Almost they are planning for, like, in next 2-3 years they are planning for actual space mission. So this is how NASA is gonna tackle the Mars mission, because like any NASA's system that you are seeing about like actual Mars mission, they always have this, because without it, flat or forget what, solar cells are not powerful enough. So that's how they're gonna achieve it. So what we can expect in the future? One thing you have to understand, we have to deal with moon first before we can even think about it, before we even imagine anything like Mars mission. We have to manage moon, and we have to do it very well, because it's one thing to say that we're gonna send robotics equipment that are gonna go there and make basically 3D printed habitats. Awesome, but how the heck you gonna test it? Now you're like, are we gonna test it on Earth? You can't test it on Earth. Elon Musk was also saying something else, like, if we find something suitable analog for lunar dust, and then we will fire engine on it to test it. Can we fire main engines on lunar system? I'm like, that's a very inaccurate way, because even if you find a particle that is exactly like lunar dust, heck, you literally, let's say, mine lunar dust here, bring lunar dust from Earth, the Earth's gravity is gonna hold it together much stronger. So even if you have a vacuum chamber, you cannot replace the gravity. So that's one of the things. The only way you can test all those things is be in a lower gravity well. The only place we can do that is moon. So another aspect is Elon time. Every Tom, Dick and Harry who does not understand Elon Musk or have been following Elon Musk for long enough, because I've been following him for long enough where I know he was trying to land on Mars by 2020, and this is 2021. He has only managed to reach to low Earth orbit in this point in time, and then it's like, 2024 moon mission, yeah, not happening. That's Elon timeline. Heck, even Elon knows that at this point. That's a bit optimistic. It's not bit optimistic, it's like ludicrously optimistic. So let's be real here. It's not going to happen anytime soon. It's going to take a lot of system, and then we need a lot of subsystems that we don't think about. We think about rocket, done. No, hell no. Like, we need much bigger variant of Moxie, and God help you, like, how the heck you're going to provide water? Like, I don't even want to think about it. It's like people are, are we going to have water on Mars? We don't have water on Mars. You can't just go there. It's like, oh, there is a lake, we're gonna drain water from there. It's like there is no place where you can do the ice subsurface. How deep you have to do, and like how deep, how much ice is mixed there, and how much is there. Like, all those things that can only be known once you're actually in there, and then you will be stuck there. So fundamentally, we need a lot of subsystem to be developed, and we need spinning habitat if we cannot shrink the time down. And even if you shrink the time down, you may have a scenario where it's like, hey, this system remains in space, even on low Earth orbit, even on basically Martian orbit, and people stay there, like for a ground communication system. And let's say you are landed on multiple places, this sort of system will act as a very good, watchtower. So having gravity, basically spinning gravity there, awesome. 3D printed habitat, awesome. We have to have all these things sorted before we plan to do Mars mission, because otherwise all our Mars mission would be is like a lucky draw. You could luck out, but most likely won't. So at best case scenario, 2050, if we are ludicrously lucky. So temper your expectations, and do focus on moon at this point in time, not on Mars. Mars is too far away. So this was my presentation on Martian mission of humans. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.